number 4. Okay, let's have a look at this now. It says Jacob has 4 coins. One of the coins is biased such that when it is thrown, the probability of obtaining a head is 7/10. He has 4 coins in total. One of them is biased. And the probability of head for that coin is 7/10. The other 3 coins are fair. Fair means they have equal probabilities of heads and tails. Jacob throws all 4 coins once. The number of heads that he obtains is denoted by the random variable x. The probability distribution table for x is as follows. Show that a equals 1/5 and find the values of b and c. Okay, now how can we do this? We need to find the probability of getting 1 heads, right? Because that it says the number of heads is what they're calling x. Okay. Now, how do you think about this? We need to find the probability of getting 1 head, 2 heads, and 3 heads. How do you find each of those 3 cases? Let's think about this. There are 4 coins. How can you get 1 head? 1 head is possible if the first one is a head, the second one is a tail, the third one is a tail, and the fourth one is also a tail. Right? Now we are assuming the first coin is the biased one, and then the remaining ones are fair. What would be the probability that you get in this case? So for now, what we're doing is probability of x being equal to 1. How can we get 1 head? All right, that's what we're trying to find out. If the first one is heads, what's the probability of that? Probability of the first one being heads is 7/10. And then for the remaining 3, the probabilities are 1/5 for each of them. So 7/10 into 1/5 into 1/5 into 1/5, you can say that's 1/5 raised to the power, sorry, why 1/5? 1/2. 1/2 raised to the power 3, right? Because 1/2 into 1/2 into 1/2, that will just be 3. Now, that's one possibility. Then another possibility could be that the first one is a tail and the second is a head, the third is a tail, the fourth is a tail. What would you get in that case? If the first one is a tail, what's the probability for that? 3/10, right? That's the biased point. And then the probability for the second one being heads and the third being tails and the fourth being tails, they're all the same because they're fair coins. These probabilities are all the same. It's going to be 1/2 into 1/2 into 1/2. That's 1/2 raised to the power 3. And if you think about it, you're going to get the same result from TTHT as well, and also TTTH. All of them are going to give you the same result. This one that we had for the last case. You can add these cases together and you would get the result. Okay, you can see what this turns out to be. What's this number? 1/5? Yeah, so it should turn out to be 1/5. That's what they wanted from us eventually. So this turns out to be 1/5. And that's the value of A that we were looking for, right? That's A. That's what we had to find in the first part. Okay. Now, what about probability of getting 2 heads? Let's think about that case now. When you have 2 heads, how can you get 2 heads? How is that going to be possible? It could be that the first one is heads and the second is tails. First is heads, or let's actually do it like this. Heads, heads, tail, tails. Now you can think of how many total possibilities there are going to be for this. If you remember your permutations well, in how many ways can you arrange these 4 letters? 4 factorial over 2 factorial and 2 factorial. There are going to be 6 cases for this one now. Okay, for this one you would have 6 cases. Now that will be a lot to list down. So let's actually think about how we can, just like we did for the previous case, we had 3 cases that were the same. and then one case that was different. We could do something similar here as well. Okay, HHTT, what's the probability for that? 7/10 for the first one. And then for the remaining, we have 1/2 whole cube, right? Because these are all fair coins. And then what are the other possibilities? With the first being head, the remaining coins could be tail, head, tail, or they could be tail, tail, head. All of these are going to be the same, right? Because only the first one is biased. So if the first is head, the probability of first is 7/10. The probability of the second, third, and fourth, they are all 1/2. So they're all the same. What we can do is we can just multiply this probability by 3 because we have to add it 3 times. We say, let's just multiply this by 3. Okay, that will give us this probability. And then another possibility could be that the first one is a tail, the second is a tail, and we have head and head. With the first being tail, how many possibilities do you have? For the second, third, and fourth, you could have tail, head, and you could also have tail, head, tail. Now for this one, if the first coin is the tail, the probability for that is 3/10. And for the remaining ones, we've got 1/2 whole cube. And now it's going to be the same for all of for both of the other cases as well. So we multiply this by 3 as well. That's going to give us a result. We add these two cases together, and that will be the probability of x being equal to 2. And that will be the value for b. Okay, you can see what this turns out to be. 0.5 raised to the power 3 multiplied by 0.7 multiplied by 0.3. So the first one is turning out to be 0.2625 for me. And then 0.3 into 0.5 raised to the power 3 multiplied by 3. The second one is 0.1125. You add these two cases together. And that gives us 3/8. Yeah, so that's what we get. 3/8 from this. This is what we get for the value of b. Okay. So this was a. And now this is b. And then we've got the last case when we want 3 heads. Now that's straightforward. Once we've got the values of a and b, how can you find c? The total probability is going to be 1. So we subtract from 1 all of these other numbers. So we know the value for a. The value of a is 1/5. The value of b is 3/8. C can now be found like this. We can say C equals 1 minus 3/80. That's the probability of 0. Minus 1/5, the probability of x equals 1. And then 3/8, the probability of x equals 2. And 7/80. And that will give you the value for C. Or you can do it directly as well if you want. You can make 4 cases for that as well. And you get the result for that. Okay, let's see what this turns out to be. 1 minus 3/8 minus 1/5 minus 3/8 minus 7/80. And that's giving me, let's check this again. 1 minus 3/80 minus 1/5 minus 3/8 minus 7/80. That's 3/10. Okay, so for C, I'm getting 3/10 or 0.3. That's the value that we've got for C here. Is that okay? Can somebody confirm this as well? Right? Okay, good. Now we need to find the expected value of x. How do you do that? For this, you just have to use the formula sigma xp. I'm sure you can all do that. Right? This part is straightforward. Expected value of x is just sigma xp. You can evaluate this. You've got the probabilities, you've got the values of x, multiply them together, then add them up together, you will get the result. Okay, what's the result for expected value of x? That's giving me 11/5, right? 11/5. It's just a one marker, so you can just write down the answer directly as well, and that's okay. In decimals, that's 2.2. However, if they're approximately symmetrical, then we say that they're close to each other. They're not necessarily going to be equal, but they're fairly close to each other. But if it's perfect symmetry, like in normal distribution, or if it's another diagram that is perfectly symmetrical, in that case, the mean and median could be exactly the same as well. Otherwise, generally, we would say they're close to each other, but not exactly equal. Okay. All right. Now, let's look at this one. Question number 6 part. It says a factory produces chocolates in 3 flavors, lemon, orange, and strawberry in the ratio 3:5:7 respectively. Nell checks the chocolates on the production line by choosing chocolates randomly one at a time. Find the probability that the first chocolate with lemon flavor that he chooses is the 7th chocolate that she checks. Okay, and now does that remind you of something? First chocolate with lemon flavor is the one that comes the 7th time she checks it. That looks like geometric distribution, kind of, but do we need to check, are the conditions satisfied for geometric distribution? What are the conditions for geometric distribution? There should be 2 outcomes. We could formulate it as 2 outcomes. We could say, this is what we're calling a success, getting a lemon flavor. And then everything else is a failure. Okay. Now, what about probability of success and failure? What about probability of success? Probability of success is going to be the lemon flavored chocolates are in this ratio, 3 ratio. So the 3 flavors are in this ratio, lemon, orange, and strawberry, 3:5:7. What about the probability of success here? What's the sum of these numbers? 8 and 7, that's 15. Probability of success would be 3 out of 15, or you could say 1 out of 5. What about the probability of failure then? That will be 4 out of 5. Now, do these probabilities remain constant? Now, that is something that you need to understand here. Do they remain constant or do they not remain constant? How do we figure that out? If it was just 15 chocolates, then we would say if you are taking out chocolates one after the other, what happens is the number of chocolates keeps getting reduced, right? So the first time getting a lemon flavor, the probability of that would be 3 out of 15. And then depending on what you got the first time, the total number would change, and the probability of whatever you're getting the second, and that will also change, right? If the number was just 15. However, we're talking about a factory. In a factory, the number of chocolates that they're producing on this production line, that is supposed to be fairly big. Okay. So it's not going to be actually just 15 chocolates. It will be something much bigger. So maybe something like 150,000, right? Something very big, basically. So out of 150,000, what's the probability of getting a lemon chocolate? That will be 30,000. 30,000 over 150,000. Now, even if you take one chocolate out from this, what's the probability of getting a lemon chocolate the next time? 29,999 divided by 149,999. The second time, the probability of getting a lemon chocolate, given that you got a lemon chocolate the first time, this number, evaluate this on your calculator. The first was 0.2. This number is also still very close to 0.2. It will be 0.199999 something. The probabilities would not change by a significant amount. Because of that, we can actually assume that approximately the probabilities are remaining constant. Okay. And generally you do this in cases when sometimes they will tell you that the data is large. If the data is very large, it means the probabilities here are going to remain fairly constant, right? They're not exactly constant, but they're not changing by a very significant amount. So we say since that change is negligible, we consider the probabilities to be constant. Now, why are we considering that? Because remember, there's a condition for geometric distribution, and the probabilities have to remain constant. So since it's a factory which is producing a large number of chocolates, we can say the probabilities remain constant, right? They remain fairly constant in this case, even if you are not replacing the chocolate after taking it out. And that's a concept that applies to a number of other problems like this as well. And they will tell you that the data is large enough. And when the data is large enough, you can use this idea. Okay, that the probability would not change. So that means we can treat this as a geometric distribution. If it is a geometric distribution, what does that mean? We need to find the probability that the first success comes on the 7th attempt. X equals 7. What's the formula for a geometric distribution? It's q raised to the power r minus 1 times p. Q is 4 over 5. So 4 over 5 raised to the power 7 minus 1, which is 6, into 1 over 5. And that should give you your result. Okay, you can see what this turns out to be. Can somebody tell me the result from this? Okay, 0.0524. That is what we get. Okay, that's the first part. Now it says find the probability that the first chocolate with lemon flavor that he chooses is after she has checked at least 6 chocolates. First success comes, the criteria for success is still the same. Getting a chocolate with lemon flavor, that's still the criteria for success. So we are saying probability of success is still 1 over 5. Probability of failure is still 4 over 5. What's the probability that the first success comes after she has checked at least 6 chocolates? We are looking for a probability of x being greater than or equal to 6. Probability of first success coming after on or after the 6th attempt. Now, what's that? X greater than or equal to 6. How do you think about this? Let me read the question statement again. After the first chocolate with lemon flavor is after she has checked at least 6 chocolates. Okay, so this could actually be taken 2 ways. So if it says after she has checked at least 6 chocolates, that means she has already checked 6 chocolates, and then the first success comes after that. That is one possibility, right? Or let me think about it, what this question statement would mean. The first chocolate that he chooses is after she has checked at least 6 chocolates. Now, if it's after she has checked at least 6 chocolates, that means we should probably not be including the 6th one here. Yeah, I think that's what it would mean, because they're using the word after here. So she has already checked 6 chocolates, and then the first time she gets a lemon flavor, that would be x greater than 6 then. Does that make sense? Now, even though this phrase here generally means that you have to include 6 as well, but then they're saying after here as well. So that means that I'm not sure if it's he or she, he has already checked 6 chocolates, and then the first success comes after that. Okay, so we could say x greater than 6. What does that give us? What's the formula that we know for this? Probability of x greater than r, that equals q raised to power r. What do we get from that? Q is 4/5 raised to power r, which is 6. And that should give you the result. You can see what that turns out to be. 4/5 raised to power 6. And that's giving me 0.26214. To 3 significant figures, that could be 0.262. Okay? Yeah. So this question statement was quite confusing, actually, because they used these two different terminologies. They said after, and then they said at least 6. So that means after they have already checked 6. So it should be x greater than 6 then. Okay, now let's move on. It says surprise boxes of chocolates each contain 15 chocolates. 3 are lemon, 5 are orange, and 7 are strawberry. Petra has a box of surprise chocolates. She chooses 3 chocolates at random from the box. She eats each chocolate before choosing the next one. Find the probability that none of Petra's 3 chocolates has orange flavor. Now, notice the difference between this part and the previous one. Remember, here we had a factory, and we assumed the supply of chocolates to be kind of unlimited, right? So the probability of getting a certain flavor was not changing. It was not changing significantly. So we assumed the probability to remain constant. But now it's not a factory that we're talking about anymore. We're talking about one box of chocolates. That's a limited number of chocolates. Okay? Now the probabilities are going to change. When you take out one chocolate, the probability for the next one would change based on that. Okay? Now she has one box and that has these chocolates in it. She chooses 3 chocolates at random. She eats each of them before taking out another one. Find the probability that none of the chocolates that she chooses has an orange flavor. Okay, now what's the probability of not selecting a chocolate with orange flavor the first time? The first time she selects a chocolate, what's the probability that that's not orange? There are 15 chocolates in total. Probability of getting an orange chocolate is 5/15. What about the probability of getting a chocolate that's not orange? 10 out of 15. That's the probability the first time. And then the second time, how many chocolates does she have left that are not orange? 9 out of how many? Out of 14. And then the next time, 8 out of 13. And that should give you the result. Okay, what do we get from this? 0.264. That's the final answer that we have. Okay, let's move on. It says find the probability that each of her 3 chocolates has a different flavor. Okay, now she wants a different flavor every single time. Now, what does that mean? She has 3 chocolates and their flavors have to be different. Now, there are 2 ways of thinking about this. One way to think about this could be using a tree diagram. You could say, okay, first time you have an orange or lemon or strawberry, right? These are the 3 flavors, lemon, orange, and strawberry. And then the next time, again, you have 3 options here, 3 options here, 3 options here. And then you have 3 options here, 3 options here, 3 options here, with all of them, with each of them. Okay. Now she wants the chocolates to have different flavor. That means one of them has to be lemon, and another of them has to be orange, and then another of them has to be strawberry. What's the probability that she gets a lemon the first time? 3 out of 15. Right? And then what's the probability of getting an orange the next time? Orange chocolates are 5. out of how many now? 14. And then the third time getting a strawberry, that is 7 out of 13. Right? However, this is only going to give you probability for one path on this tree diagram. Lemon, orange, and then strawberry. This is one path on this tree diagram that you have found the probability for. There are other paths as well. You could have orange first, and then lemon, and then orange. And then strawberry. Orange, lemon, strawberry. You could have lemon, strawberry, orange. There are many different pathways like that. How many different paths like this exist on this tree diagram? The number of arrangements that you have for LOS. In how many ways can you arrange LOS? Right? You could have lemon the first time, orange the second time, strawberry the third time, or you could have LSO, or you could have SLO or SOL, and similarly and so on. How many total arrangements do you have for this? Because that's how many paths you would have on this tree diagram that you would have to consider. There are 6 ways of arranging this, 3 factorial. So you say each of these probabilities is going to come in 6 places on this tree diagram. You have to add all of those cases up. Instead of adding, we could just multiply this by 6, and that will give us the result. Make sense? Because every time the numerator is going to have 3, 5, and 7. Right? These were the three numbers that we have in the numerator. And every time in the denominator, we would have the same 3 numbers, 15, 14, and 13. So we just multiply by 3 factorial because that's the total number of cases that we got in that tree diagram. Okay? This only considers one of those paths. So you have to consider the other paths on the tree diagram as well. This is one way to think about this. Another way that's simpler is using combinations here. And that is, there are 15 chocolates in total. If there were no conditions and you had to select how many chocolates? 3 chocolates. In how many ways can you do that? 15C3. Out of 15, select 3 chocolates. But then you've got some conditions. The conditions are, you need 3 different colors. That means out of 3 lemon chocolates, you need 1. Out of 5 orange chocolates, you want 1. Out of 7 strawberry chocolates, you want 1. So in the numerator, you could have 3C1 and 5C1 and 7C1. And that should give you the same result as well. You can see what this turns out to be. Okay. What's this number? 3/13. 3/13. Or you can write this in decimals as well. And that's your probability. Make sense? No problems? Okay, let's move on to the next one now. Now it says find the probability that at least 2 of her chocolates have strawberry flavor, given that none of them has orange flavor. Now this is conditional probability. None of them should have orange flavor. Okay, now let me write that down. Probability at least 2 strawberry chocolates, given that there are no orange chocolates. Now, the case that is given, that should be in the denominator here. This should be in the denominator here. And in the numerator, we have what is common to both of them. The probability of both of these conditions being true at the same time. Their intersection, basically. Probability that you have at least 2 strawberry and there are no orange chocolates. In how many ways can we do this now? We have already calculated the probability of having no orange chocolates above. Probability of having no orange chocolates was 0.264. Or you can use an exact number for this, whatever that exact number was. What was this exact number? Okay, so this exact number was 24/91. So it's better to use that exact value, 24/91. That is going to be your denominator here, 24/91. And what about the numerator here? Where both of these conditions are met, at least 2s and no orange chocolates. Now, how do you find this case? At least 2s and no orange chocolates. Okay, now there are 5 orange. You want none of those 5 chocolates, the ones that are orange. And out of the remaining, you want there to be at least 2s. Now, what are the possibilities that you could have? If you want at least 2s, one possibility is, let me do that on the side. You have S, and lemon, or you have SSS. These are 2 conditions, right? These are 2 cases that satisfy these two conditions. Find the probability for each one of them. Okay, there's azan going on here. Just write it down. I'll explain it in a minute. So, in a minute. Okay, I'm sorry. Okay, SSL. So the one possibility is that you have 2 strawberry chocolates, that's 7C2, and 1 lemon chocolate, that's 3C1. Out of 3 lemon, you have 1. The other possibilities, you have all strawberry. So it's basically an OR case, not AND. So it's either this first case or the second case, right? These are the only 2 cases that you can have that satisfy both of these conditions. That you have no orange chocolate, that condition is satisfied, and you have at least 2 strawberry. That means you could have at least 2, you could have exactly 2 strawberry chocolates or 3 strawberry chocolates. Those are the 2 cases that we're considering here. SSL or SSS. Okay. Any one of these 2. That is what your numerator is going to be. That's 7C2 multiplied by 3C1 plus 7C3. That's your numerator, and that should give you the result. You can see what that turns out to be. What's this number? 98 divided by 24/91. Is that what you're saying? Okay, no, I'm sorry. In the denominator, yeah, so you're right. In the denominator, we considered probability here. We mixed up those 2 things. What about, so in this case, we should be looking at number of combinations for both of them, right? No orange chocolates. When was that possible? When we could get no orange chocolates? There were 15 total chocolates. If we want none of them to be orange, we have 10 chocolates that are not orange. Out of those 10, in the numerator here, we should not have a probability. Instead, we should have number of combinations. We do not want any orange chocolate. So out of the remaining 10, we want 3 chocolates. That will be 10C3. What's the denominator? 10C3. That's 120. 98 over 120, that simplifies to 49 over 60. And that's your probability that you're looking for. Okay. In combination method, we don't have to worry about arrangements, right? We're just selecting them. Here as well, it's not the arrangements that we are considering, because the arrangements don't matter. Arrangements do not matter. Do not get confused by 3 factorial that we're actually considering arrangements of this. It's basically, we are considering the different arrangements here for the reason that on the tree diagram, we have 6 different paths that can give us the same condition, that the 3 chocolates are different. So this 3 factorial was used basically to reduce our working, that we don't have to calculate all of those cases separately and then add them together. We said, okay, we could use our permutation concepts to figure out how many different paths like this would be there on the tree diagram. That's 3 factorial paths. To reduce that working, we just multiplied this by 3 factorial. It's not that we are considering arrangements of these chocolates. Arrangements do not matter. It's just that on the tree diagram, you have multiple cases that you have to consider. How many such cases exist on that tree diagram? To find those number of cases, we use 3 factorial here. Otherwise, arrangements do not matter. That's why when we do it like this, we're using combinations here rather than arrangements. Is that okay? Because if you want different flavored chocolates, it doesn't matter which one comes first, which one comes after. That's irrelevant here. But the tree diagram gives us different paths, so we have to consider all of those paths. For calculating how many paths like that exist, we do this 3 factorial thing here. Okay. So in the combination method, you would not be considering any arrangement here. Make sense? Yes? Okay, let's go back to this paper. Question number 5 from this paper now. A red spinner has 4 sides labeled 1, 2, 3, 4. When the spinner is spun, the score is the number on the side on which it lands. The random variable x denotes the score. The probability distribution table for x is given below. Show that p equals 0.12. Now, these are all probabilities. The sum of all probabilities has to be 1. So we say 0.28 plus p plus 2p plus 3p, that has to be equal to 1. You can find the value of p from this. 1 minus 0.28 divided by 6, that's 0.12. Yeah, in fact, you have to find that. So p equals 0.12. That's the value of p. Now it says a fair blue spinner. Okay, so we had a red spinner first. It had 4 sides labeled 1, 2, 3, 4. Okay, so we have this red spinner. The score is the number on the side on which it lands. X denotes the score 1, 2, 3, 4. We have this probability distribution table of X. Okay, all right. A fair blue spinner. Now we have another spinner that's blue. And a fair green spinner have 4 sides labeled 1, 2, 3, 4. As before, all 3 spinners are spun at the same time. So we have 2 other spinners and they are the same. It's just that it says that their colors are different. Find the probability that the sum of the 3 scores is 4 or less. Sum of the 3 scores is 4 or less. Now, what are the possibilities? On the first, from the first spinner, you could get 1, 2, 3, 4. From the second spinner, you could get 1, 2, 3, 4. From the third spinner, you could get 1, 2, 3, 4. You can't make a table for this. This is 3 events. You can only make a table for 2 events. For 3 events, it would be a 3-dimensional table that you can't really draw on a paper. You could think of making a tree diagram if you wanted, but that would be too big. 1, 2, 3, 4. then with each of them, you have 4 more branches and then 4 more branches. That will be 4 into 4 into 4. That's 64 branches in the last step. So making a tree diagram would also not be helpful. So you should do it directly just in your head. How would you do that? All the spinners have sides numbered 1, 2, 3, 4. All right. We want the sum of the 3 scores to be 4 or less. What's the total number of possible outcomes, first of all? Probability is number of favorable outcomes divided by the total number of possible outcomes. What's the total number of possible outcomes? 4 into 4 into 4, that's 64. So the denominator is going to be 64 when we find this probability. What about the numerator? How many of those 64 different cases satisfy the given condition? Sum is 4 or less. Now, you can actually just list them down because there are not many of those cases. You could have 1, 1, 1. That's one possibility. You could have 1, 1, 2. You could have 1, 2, 1, or you could have 2, 1, 1, and that's it. There's no other possibility, right? So there are 4 cases. Favorable outcomes are 4. There's no other case apart from this. So that's 4 out of 64, and that gives you 1 over 16. That's the probability that the sum of the 3 scores is 4 or less. Make sense? Muslim, it's going to be 4, not 6. You cannot count this 3 times if that's what you're doing. This is only one outcome. Okay, so 4 out of 64. Okay, now it says find the probability that the product of the 3 scores is 4 or less given that X is odd. Okay. Given that X is odd, what kind of probability is this? This is conditional probability. What is X? X is the number that came on the red spinner. X is supposed to be odd. That means X is either 1 or it's 3. These are the only 2 possibilities that we have for X. Now, we know the probability for 1, that's 0.28. Oh, you're right. I'm sorry about this. So we missed something here. This is not correct. Thank you for pointing that out. So this is not correct. Part B is not correct. We had to find the probability of sum of the 3 scores being 4 or less. Now we could do this if all the spinners were fair. Now these are not fair spinners. Not all of them are fair. So we missed that here. I'm sorry about it. The first spinner, the red spinner, that is not fair. It has different probabilities. If we could only do this if the first spinner was also fair. In this case, it's not fair. So we would have to find the probabilities of each of these cases separately then. We can't do it directly because favorable outcomes divided by possible outcomes is only done when the probabilities of all outcomes is the same. Here, the probabilities of all outcomes is not the same. So thank you for pointing that out. Let's assume we have these 3 spinners like this. The first is red, let's say, and the second is maybe blue, and then you have green. These are the possible outcomes you could have. Okay, these are the possible outcomes. Now, what is the probability of 1, 1, 1? How would you calculate that probability? Probability of getting 1 on the red spinner. What's that probability? That's 0.28. Let's actually fill out this table as well now. This is going to be 0.12. This is going to be 0.24. This is going to be 0.36 because we know the value of P is 0.12. So what's this probability? 1, 1, 1. Probability of red being 1 is 0.28. So this probability is going to be 0.28. And the blue spinner being 1 we have 4 possible outcomes. One of them is 1. So that's 1/4. You could say 0.25 or 1/4. And then similarly for green, it's 1/4, that's 0.25. That's the first case. Okay. Then 1, 1, 2. So you have 0.28 for red, and then 0.25 for blue. And then for green, if you have 2 as well, that probability is still 0.25. Again, in the third case as well, we have 0.28, 0.25 into 0.25. The last case is going to be different because now we have 2 on the red spinner. That probability is 0.12. So that's going to be 0.12 into 0.25 into 0.25. So from the other 2 spinners, all probabilities are 0.25. In the first spinner, the probabilities are different. So you have to be careful about that. You find each of these separately and then add them up together because it's either the first case or the second case or the third case or the fourth case. So you add all of those probabilities up. And that's going to give you the result. Okay, so you can calculate one of them and then multiply that by 3. 0.28 into 0.25 into 0.25, that's giving me 0.0175. This is also going to be 0.0175. This is also going to be 0.0175. And the last one is going to be 0.12 into 0.25 into 0.25. That's 0.0075. Now you just add all of these numbers and that gives you the result. Let's see what this turns out to be. 0.0175 into 3 plus 0.0075, and that turns out to be 3/50, which is 0.06. So this is actually 0.06. That's the probability that we get from this. Yeah, thank you for that. How is it 0.25? It's a blue spinner and green spinner. They are fair spinners. There are 4 sides. So each side has 1/4 probability. That's 0.25, right? If it's a fair spinner, all sides have equal probability. So that's 1/4, 1/4. So 0.25 for all of them. All right, so that's the probability that we get in the second part. Now it says find the probability that the product of the 3 scores is 4 or less, given that X is odd. Now this is conditional probability. How do you find conditional probability? Remember the formula for that? Probability of A given B, that is equal to probability of A intersection B divided by probability of B. Or you could just remember it in words as well. In the numerator, you have the probability of both happening at the same time. Probability of both divided by the probability of what is given, right? Both together, that's what you have in the numerator. Probability of both events happening at the same time. In the denominator, you have the probability of what is given. That's how you find conditional probability. Now, what do we do here? What is given? It's given that X is odd. Let's find that probability first. Given that X is odd. Probability that X is odd. What is that probability? X is odd when X is either 1 or it's 3. These are the only 2 possibilities, right? It could either be 1 or it could be 3. What's the total probability for these 2 cases? It's 0.28 and 0.24. Just add those 2 numbers up. What does that give you? 0.28 plus 0.24? That gives you 0.52. That's going to be the denominator. This is the probability of what is given, right? Let me actually write the formula here. So what you want is, in the numerator, you would have probability of X odd and what's the second condition? Score is 4 or less. Product is less than or equal to 4. Both of these conditions have to be met. In the denominator, you have that x is odd. So we have found the denominator. The probability of the denominator is 0.52. Okay. Now, out of these cases, when x is odd, when is the product 4 or less? When is the product of the three scores 4 or less? We need to find this now. Let's think about this. Now we know that x is supposed to be odd. So what are the possibilities that we have for x? It could either be 1 or it could be 3. These are the two possibilities. Keep that in mind. So x can either be 1 or it can be 3. Now, what about the other two boxes, the other two spinners? One spinner is blue. You could have 1, 2, 3, 4, anything from there. And the other is green. You could have 1, 2, 3, 4, anything from there. Blue and green, right? Yeah. Now, how many cases do we have when the product is, which cases do you have when the product is less than or equal to 4? Let's list them down. So if x is 1, what possibilities could you have for blue and green? Both of them could be 1, right? That satisfies the condition. With x being 1 and b being 1, so do it in a structured way so that you don't miss out in any possible cases. So find all the possible cases with x and b equal to 1. So with x and b 1, g could be 1, it could be 2, it could be 3, it could be 4. So you have all of those possibilities for green, and the product would be less than or equal to 4 in each of them. Okay. Now, what if x is 1 and b is something else, b is 2? What happens in that case? With 1 and 2, you could have 1 here, and with 1 and 2, you could also have 2 here. And then you have 1 and 3, that's too many cases. Okay, 1 and 3. With 1, 3, the last one can only be 1. It'll be 1. These are all the cases that you have with x equal to 1. And now you have to think about the case when x is 3. What about that now? With x3? When x is 3, b could be 1 and g could be 1. And 3, 1 could not give us anything else here. 3, 1, 2, yeah, no. And this could also not be anything else. Yeah, so with 3, we only have one case. Okay. The product needs to be less than or equal to 4, right? So 1, 1, 4, 1 into 1 into 4. How, Ali, what are you doing? 1 into 1 into 4, that's 4. How is that more than 4? They are multiplied. We're multiplying them, not adding them, okay? All right, so these are all the cases that we've got. Now we have to find the probabilities. How do you do that? All of these probabilities, remember, are 0.25. All of these are 0.25. Only probability of x is different. Probability of x being equal to 1 is 0.28. So in all of these cases, 0.28 into 0.25 into 0.25, in all of these first few cases, we're going to have the same probability, 0.28 into 0.25 into 0.25. All of these are the same. Only the last one is going to be different, because then the probability of 3, x being equal to 3 is 0.24. So you use that here. It's not 0.12, it's actually 0.24 into 0.25 into 0.25. And that gives you the numerator of in that formula that you will be using. Let's see what this turns out to be. Add all of these numbers up and see what that gives you. You can count how many cases we have. 1, 2, 3, 4, 5, 6, 7, 8. So 8 into this number. Let's see what that turns out to be. 8 into 0.28. into 0.25 into 0.25 plus this last case, which is 0.24 into 0.25 into 0.25. That's giving me 0.155. Can somebody confirm this as well? 0.155, that's what I'm getting. Right? Okay, good. So this is the numerator then. This is the denominator. Now we can just input these values in that formula. What's the probability that we are looking for? This is this denominator, and this numerator is what we have found here, right? Where both of those conditions are met. So the probability that we're looking for, that's 0.155 divided by the probability of x being odd, which was 0.52. That's what you have in the denominator here, and that's going to give you the result. Okay, so we get 0.298 for this. That's our final result, 0.298. One. Now we've got question number 7. Sharma knows that she has 3 tins of carrots, 2 tins of peas, and 2 tins of sweet corn in her cupboard. All the tins are the same shape and size, but the labels have all been removed. So Sharma does not know what each tin contains. Okay. So we've got 3 tins of carrots and 2 tins of peas. And then we have 2 tins of sweet corn. Acha. So Sharma wants carrot for a meal, and she starts opening the tins one at a time. Okay. Chosen randomly until she opens a tin of carrots. The random variable x is the number of tins that she needs to open. The number of tins that she needs to open until she gets a tin of carrots. Okay. Number of tins that she needs to open until she gets a carrot. Okay. Now it looks like what distribution does it look like? Any guesses? आपका start में शायद आपको लगे it's very similar to that actually. You're looking for the first success, aren't you? You're repeating something. आप एक चीज करते जा रहे हैं बार-बार, and you're looking for when your first success comes. पहली दफा आपको success कब मिलती है? Success क्या है यहाँ पे? Opening a tin of carrot. That's the success. That's what you're looking for, right? लेकिन यहाँ पे एक मसला है. मसला क्या है? Probabilities constant नहीं रह रही हैं. Probabilities आपकी constant नहीं रह रही हैं. Probabilities change हो रही हैं, right? तो यहाँ पे geometric distribution हम अप्लाई नहीं कर सकते because probabilities constant नहीं रहती हैं. उसकी दूसरी condition meet हो रही है कि we're looking for the first success. First time success कब आ रही है? That's met. That condition is met. लेकिन probabilities constant नहीं रह रही है. ठीक है? So that's why you can not use that. इसको basically आपको logically देखना पड़ेगा. क्या करेंगे? Third attempt में उसको carrot मिली. ठीक है? 10 of carrot मिला. That means the first cupboard that she opens, the first tin that she opens, that is not a carrot. The first is not a carrot. The second is also not a carrot. And the third then is a carrot, right? Yeah, it isn't binomial either because basically उन दोनों के लिए आपको क्या चाहिए होता है? Probabilities constant रहनी चाहिए. यहाँ पे probabilities constant नहीं रह रही, right? क्योंकि आपने जब first tin open कर लिया, आपके पास the number of tins रह गए, बाकी वो कम हो गए. Let's think about this. First tin में carrot नहीं होने की probability क्या है? You got 7 total tins. उनमें से कितनों में carrots नहीं है? 4 में carrots नहीं है. So what's the probability of not having a carrot in the first tin? That is 4/7. Okay. What's the probability of not having a carrot in the second tin as well then? एक tin तो आपका निकल गया. बाकी कितने रह गए आपके पास? 3 carrots वाले रह गए, 3 non carrots वाले रह गए. So the second probability क्या हो जाएगी? 3/6. And then the probability that you get a carrot in the next attempt, carrots वाले कितने 10 boxes हैं अभी? आपके पास अभी भी 3 हैं. लेकिन total कितने रह गए हैं? 5 रह गए हैं. We've got this. We just multiply these probabilities and we get the result from this. या देख लें आपके पास क्या आता है. So this is x. X, remember यहाँ पे क्या represent कर रहा है? Let me just highlight that. X is representing the number of tens that she needs to open. So अगर 3 tens open करने के बाद उसको कैरेट मिलती है, उसका क्या है कि फर्स्ट 2 में कैरेट नहीं मिली, थर्ड में कैरेट्स मिली. So probability of x equals 3 आपके पास क्या होगी? That's going to be this. इसको evaluate कर लें, देखना आपके पास क्या आता है. 4 divided by 7 into 3 divided by 6 into 3 divided by 5, and getting 6 over 35, and that's what we wanted to prove there. 6 over 35. Acha, now it says draw up the probability distribution table for x. अब 3 वाली calculations आपसे करवा ली है, अब आपको एक पूरा table बनाना है to write down, and you have to write down all possible values of x. ठीक है? अच्छा. And their corresponding probabilities, of course. What I'm going to do is I'm going to draw a table first. The table may look something like this. Draw that on the side here first. Okay, this is the table. And now we need to think about what values of x do we have possible. X के क्या-क्या values हो सकते हैं? X क्या represent कर रहा है? Again, the number of tens that she needs to open to get a 10 of carats. हो सकता है उसको first time मिल जाए. X की एक value 1 हो सकती है. हो सकता है second time मिल जाए, third time मिल जाए, fourth time मिल जाए, fifth time मिल जाए, and then 6th and 7th as well. What do you think? Carats कितनी है? Carats वाले tens कितने? We've got 3 carats in total. 3 carats tens in total, right? अगर आपने 5 tens already खोल लिए हैं, और let's say 4 tens already खोल लिए हैं, 4 tens already खोल लिए हैं, और आपको carats नहीं मिली हैं, तो 5th तो definitely carats वाला होगा, right? उसके बाद आपको खोलने की जरूरत नहीं पड़ेगी, right? Because बाकी तीनों carats के रह गए, तो 5th तो definitely carats का होगा, फिर अगर आपको पहले 4 में नहीं मिला, तो basically x की maximum value क्या होगी? That's going to be 5. So we don't need to go any further than that. इन सब की probabilities लिखनी है. That's a 4-mark question. How are you going to get those 4 marks? 3 वाली probability already आपने first part में निकाल ली है, बाकी आपको probabilities यहाँ पे लिखनी है. ठीक है? Okay. Now let's do that. Exactly the same logic as the first one. x1 equals 1, x equals 1 वाली probability क्या हो जाएगी? इसको यहाँ पे evaluate कर लेते हैं. इसकी working show कर देंगे तो it's going to be better. Although इसके eventually marks आपको सिर्फ table में values के मिलेंगे, लेकिन लिखने का फायदा ही होगा, हो सकता है आपको अगर values आपको सारी गलत आ रही हैं, उसके partial marks मिल जाए कुछ. अच्छा, x equals 1, आपको first time में carrot मिल गया. That's 3 out of 7, right? 3 carrots ले लेते हैं और 7 total था. 3 out of 7, that's probability of x equals 1. ठीक है, मैं यहाँ पे लिख लेता हूँ साइड्स के ऊपर. Carrots वाले tens कितने हैं? They are 3. Non-carrots कितने हैं? वो कैरेट के अलावा जो मर्जी हमें उससे फर्क नहीं पड़ता, जस्ट कंसर्न कि वो कैरेट नहीं है. नॉन कैरेट हमारे पास 4 एंड टोटल कितने हो गए? टोटल इज 7. तो फर्स्ट टाइम में कैरेट मिल जाए उसकी प्रोबेबिलिटी क्या है? 3 over 7. ओके, प्रोबेबिलिटी ऑफ x equals 2. What does that mean? First non-caret, that's going to be 4 over 7, and then second caret, that's 3 out of the remaining, that's 6. 3 over 6. ठीक है. Khizr, 5 over 15 over 35. Yeah, it doesn't matter. It doesn't matter. You can write 3 over 7 here. Margin scheme अगर 15 over 35 लिखा हुआ, that's equivalent to this. वो उसने सिर्फ इसलिए किया हुआ कि denominator सबका same हो जाए, but it doesn't matter. It doesn't matter. उससे फर्क नहीं पड़ता. They're equivalent. Okay. अच्छा. Now what do we get from this? ये evaluate कर लें. ये क्या आता है? 4 over 7 into 3 divided by 6. That's 2 over 7. Normally होता ये है कि अगर आपकी probabilities अनसिंप्लीफाइड फॉर्म में लिखी हो ना, तो उससे बस वेरिफिकेशन आसान हो जाती है, तो ऐड करके 1 आ रहा है सब में कि नहीं, वो फायदा हो जाता है। लेकिन अगर आपके पास ऑलरेडी आंसर ही इस फॉर्म के अंदर है, सिंप्लीफाइड फॉर्म में, तो उसको वापस उसमें कन्वर्ट करने की जरूरत नहीं होती, यू जस्ट लीव इट लाइक दैट, दैट्स ओके। अच्छा, x इक्वल्स 2 आ गया, x इक्वल्स 4 फाइंड कर लेते हैं। उसके फोर्थ अटेम्प्ट में उसको कैरेट मिले, यानी फर्स्ट शुड नॉट बी अ कैरेट, second should not be a caret, that's 3/6. Third should not be a caret, that's going to be 2/5. And then fourth caret, carets kitni hai? 3 out of how many? 4 that are remaining. ये आप evaluate कर लें, ठीक है? That's going to be 4 divided by 7 into 3 divided by 6 into 2 divided by 5 into 3 divided by 4, and that gives me 3/35. This is 3/35. Now, if you're absolutely sure कि ये calculation आपकी सारी सही है, फिर आप फिफ्थ के लिए क्या कर सकते हो? 1 में से माइनस कर दो सबको, okay? But if you're unsure, then it's better to evaluate that separately as well, कि in case आपका किसी और में error हो गया हो कोई, तो 5 वाली तो आपकी probability सही आ जाए, अगर आप 1 में से माइनस करके लिखोगे, तो वो अगर आपकी कोई और गलत होती तो वो सही नहीं होएगा, तो आपकी वो वैल्यू फिर ये भी सही नहीं आएगी, तो मसला होएगा। तो आप अलग से evaluate कर लें if you can, and then you can verify by adding everything आपके वो 1 पे add हो रहा है कि नहीं हो रहा। x equals 5 का क्या मतलब है? First be non-caret, second be non-caret, 3/6, third be non-caret, 2/5, fourth be non-caret, that's 1/4. अब बाकी सारी तो carets रह गई हैं, fifth should be a caret, so that's 3/3. ये evaluate कर लें, ये देख लें क्या होता है आपके पास। 4 divided by 7 into 3 divided by 6 into 2 divided by 5 into 1 divided by 4, that is 1/35. And now you can verify your calculations. In sub probabilities को add कर लें, they should all add up to 1 because the total probability is always 1. Sorry. Okay, so let's have a look at this. Question number 2 from this paper. That's the first one that you want me to discuss. Okay, so it says a bag contains 5 red balls and 3 blue balls. 5 red balls, 3 blue balls. Again, just a reminder, in S1, please make sure that you take your time to read the question statement. Do not rush into just starting with the solution. Read the question statement very carefully and a bit slowly, and that will help you not do many careless errors, okay? So you have a bag that contains 5 red balls and 3 blue balls. This person takes 3 balls at random from the bag without replacement. The random variable x represents the number of red balls that she takes. Show that the probability. Other account. Can you guys still hear me? Okay, I'm back now. Can you guys still hear me? Oh, good, thank you. Okay, so this person takes 3 balls at random from the bag without replacement. The random variable x represents the number of red balls that she takes. Show that the probability that she takes exactly 1 red ball is 15 out of 56. Okay. Now she's taking out 3 balls, right, at random. Now, what are the possible cases for her taking exactly 1 red ball? One possibility could be that she takes a red ball, and then the first time, and then the second time she takes out a blue ball, and then the third time she takes out a blue ball. And then another possibility could be that the first time she takes out a blue ball, and then a red, and then a blue. Another possibility could be that she takes blue balls the first 2 times, and then a red ball the third time. These are the 3 possible cases you would have. You can make a tree diagram for this as well, and these will be the cases that you get from that. Right? It's not going to be a very big tree diagram. We'll have 2 branches every single time. So 8 branches for the last step. That's not going to take that long. You can do that. We might actually need to do that for the next part. Yeah, probably. Okay, so RBB plus BRB and BBR. What are the probabilities now? RBB. So if you have a red ball the first time, what's the probability for that? 5/8 into blue ball the second time, that's 4/7. Sorry, 3/7. And then 2/6.
That is what we get the first time. Now, if you think about it, the numerator is always going to be 5 into 3 into 2 in each of these cases. You can write one more to confirm this. What is going to be the second case? The second case is going to be 3/8 for the first blue ball, and then 5/7 for the second for the second red ball, and then 2/6 for the third blue ball. Now think about it. In the numerator, you've got 5 into 3 into 2, 3 into 5 into 2, 8 into 7 into 6, 8 into 7 into 6. These are basically the same probabilities that you have to add. Now, a quicker way of doing this could be, for now, let me just write this as well. This is going to be 3/8 into 2/7 into 5/6. And that will give you the result. A quicker way of doing such problems is you say, okay, out of the 8 balls, let's actually consider just one scenario, RBB. What's the probability for this? 5/8 for the first time, and then 3/7, and then 2/6. And then you think about in how many ways can you arrange this? So on a tree diagram, you would have red, blue, blue. That is one possibility. That gives you 1 red and 2 blue. And another possibility would be that you have blue, and then red, and then blue. Another possibility would be that you have blue, and then blue, and then red. Right? There are 3 cases that will be there on the tree diagram. Of course, this is not the complete tree diagram, but these will be 3 parts that are giving you the same probability. So the way to do such problems is you just find the probability for one such case, and then you think about in how many parts on the tree diagram that you can find for this. We listed those parts up there. A direct way of doing this could be, you could say, okay, how many ways can you arrange this? There are 3 letters, that's 3 factorial. But then 2 of them are identical, 3 factorial over 2 factorial. This is basically 3, and that is giving you these 3 cases. So what you can do is find the probability for just one of these cases, multiply that by 3, and that will give you that final result. Okay, you can see what this turns out to be. 5 into 3 into 2 divided by 8 and 7 and 6 multiplied by 3, and that's giving me 15/56. This is one possible method. This is what you can use here. Okay. Now, another way to do the same thing is using combinations. This is one possible method. In fact, this was one possible method in which we listed down all possibilities. And then another possibility is that we just find one case, multiply that by 3. Or you could also use combinations like this in cases where you have something being taken out without replacement. In cases where you have without replacement condition mentioned, you can also use combinations. And that works like this. You can say, okay, we want exactly 1 red ball out of how many balls? Out of 1 red ball out of 8 balls. Yeah, out of 5 balls, sorry. These are 5 balls, so you're not distracted. Okay, so you have 5 red balls, you want 1 red ball, and out of 3 blue balls, you want 2 blue balls. So you can also think of it like this, that since you want exactly 1 red ball, you say out of 5 red balls, select 1 red ball, 5C1. And out of 3 blue balls, select 2 blue balls. These are your favorable outcomes, the outcomes that satisfy the given condition. Okay, that out of 5 red balls, you want to select only 1, and out of 3 blue balls, you want to select 2. Okay, can you guys still see my screen? Can you see me writing? Okay, maybe there's a lag because on my other device, I can't see that. Okay, all right. So 5C1 into 3C2 divided by the total number of possible combinations. What's the total number of possible combinations? Out of 8, we have to select 3 balls. So that's 8C3. And that could also give it the same result. You can try this. 5C1 multiplied by 3C2 divided by 8C3. And that gives you the same result as before. That is 15/56. This could be another possibility. Now, the thing is, you have to know both of these methods, both methods. The reason for that is sometimes figuring out all of these cases on the tree diagram, it becomes quite complicated. And the combination method makes it much easier. But the combination method cannot always be used. Combination method only works when you have without replacement here. If you had with replacement, that means the probabilities were not changing every time. Then you would have to think of these cases. So this method would work every time, but sometimes it gets a bit too complicated. And that is where the combination method is going to help you simplify things. Okay, but remember, the combination method will only work when this is without replacement. Otherwise, it would not work. Is that okay? Any problem with this? Because if you understand this first part, then the second part is just doing that same thing over and over again for the other possible values of x. Any problem with the first part? Because if you understand this, the second part is fairly straightforward then. Okay. Now, in the second part, it says, draw up the probability distribution table for x. That means you want some values of x and corresponding probabilities of those values of x. Now, what does x represent? X represents the number of red balls taken. What could be the number of red balls? You're taking a ball 3 times. X could either be 0, right? You might have no red ball. You could have x equal to 1, or x equal to 2, or x equal to 3. These are 4 possible cases that you have. Now, when x equals 1, what's the probability for that? We already know that. We have found that 15/56. This probability we've already figured out. What about the other cases now? Now you can use any of these methods that you prefer. I would say combination is much quicker in this case, but it's your choice. You can also do this. This also works. X equals 0. What does that mean? The denominator is going to be the same. Out of 8 balls, you want to select 3 balls. In the numerator, if you want no red balls, what does that mean? Out of 5 red balls, you select 0. 5C0. Out of 3 blue balls, you select all 3. And that will give you this first probability. That's 1 into 1 divided by 8C3. What was 8C3? 8C3 was 56 here. This is 1/56. And then probability of x equals 2. What would that be? Out of 5 red balls, select 2. Out of 3 blue balls, select 1. Divided by 8C3. And that will give you something. 10 into 3, I think that's 30/56. And then you can do the same thing for x equals 3 as well. I would recommend if calculating the probability is fairly straightforward, like in this case, calculate each of these probabilities rather than doing one minus that, because you can then verify your answer as well. So let me explain what that means. Find the probability of x equals 3 as well. Let's see what that turns out to be. That would be 5C3 into 3C0 divided by 8C3. Now 5C3 is 10. 10 into 1 divided by that, that's 10/56. Now the probabilities turn out to be 1/56 here, and then 30/56 here, and then finally 10/56. And now you can verify your answer. Add all of these probabilities, they should add up to 1. So 16 plus 40, that's 56/56. They do add up to 1. So that's most likely going to be correct, because the probabilities are all adding up to 1. And that's your probability distribution table. Okay. That's the second part of this. Then the third part, you're given that expected value of x is 15/8. Find the variance of x using that. Now, that's a standard process. You can do that, I suppose. You've got the expected value given. So all you have to do is just add another row to the data that represents x squared times p. xp is not needed because they already have given you the expected value. What's x squared p going to be? 1/56. Sorry, 0. 15 over 56. 2 squared is 4. 4 into 30 over 56, that is 15 over 7. And then 9 into 10 over 56. And that's 45 over 28. You can add all of them up. You'll get sigma x squared p from this. What's that? 15 over 56 plus 15 over 7 plus 45 over 28. And that's giving me 225 over 56. Just put that here in the formula. Variance of x. What's the formula for variance of x? It's written in the formula sheet as well. It looks like this: sigma x squared p minus expected value of x whole squared. That's the formula for variance. What is sigma x squared p? 225 over 56. Subtract from this square of 15 over 8. And that will be your variance. You can see what that is. Okay, this is giving me 225 over 448. You can write this in decimals as well. In decimal, it turns out to be 0.5022, which is 0.5022, 3 significant figures, and that's your final answer. That's what we wanted.